Alright, this is another programming video. So I want to show you what I recently did. In my last video, I showed you how I used Allegro to make a spinning polygon. In this one, I want to show you something similar. First, I'm going to clear this screen, and then I'm going to use make, and we're going to compile and run. You see what I have here? This is another spinning polygon. However, this does my checkerboard illusion. However, have you noticed how slow it's going? It's going quite slow. And there's a reason for why it's so slow. And when you see the source code, you will see why. So, let me make sure I'm actually still recording. Yes, I'm recording. Okay. So, I'm going to show you, first I'm going to show you how the other demo, because my one from my last video, my spinning polygon, I have it. It requires these DLL files. So if I double click on main.exe, see now we have, that's the speed of the simple white pentagram that spins with my original program I wrote. So this new program I wrote, why is it so slow? Well, I'm going to show you. That is unfortunately because I'm using somebody else's graphics library. Allegro, you know, it's actually a game programming library. It's made for making video games is what it's kind of for, but it could be used for all kinds of things. So I'm going to show you my full source code, or at least the parts that are relevant. So this is even bigger than my last program. It has the variables defining, it has all the include headers, it has a new header of functions I wrote, and it has 3 bitmaps. I'm going to go over briefly what it does. It creates a checkerboard where the squares are 32 pixels width, wide, and high, and it has the variables for the polygon, of course, just like the previous program does all the initialization. And it allocates memory. It creates the 3 bitmaps of the exact same size, and width and height are technically defined as global variables, but I also have them passed as arguments to these functions for future purposes. So first what it does is it draws the checkerboard. So I'm going to quickly rerun it again. I'm going to show you here. The checkerboard is the easy part. Although it took me some time to write it. So red and green is the color of the checkerboard. And you can see that I can modify the colors here. First I'm going to make the checkerboard be simply black and white. Okay. So, and then we're going to rerun this. And there it is. There it's beautiful. It's still slow, but now we're back to black and white, which are my default colors that I prefer. So now I'm going to show you the rest of the code here. So first it's creating that checkerboard with that specific black and white and square size and the width and height. So notice it sets the target bitmap to bitmap 2. Bitmap 2 is the name of the one that stores the checkerboard, and the checkerboard is only written to that bitmap once. I'm going to show you what I wrote here. Now, wait, that's the wrong file. I'm looking for Allegro BVM. Okay, so I have some functions here. I have BVM fill. This one is not actually used. This one is used, AL chastity checker. Now, this is the first clue as to why it's slow. Now, this only draws the checkerboard once, but you'll notice something. In order to draw the checkerboard, I have to have code to convert my colors, because my program stores 32-bit integer numbers that represents the colors, with the higher byte being red, next green, then blue. Very simple. Now that requires this code to convert those 2 colors into the colors Allegro understands. First it extracts the red, green, and blue components and then maps that onto an Allegro color. So that takes some time. And then it gets the current target bitmap, which in this case is bitmap 2. We know what that is, but it's not passed as an argument because it just gets whatever the current target is. And then it does my routine my routine for drawing a checkerboard is still very simple. The only difference is that now the array of 2 colors are Allegro colors and we're using AL put pixel. But here's another key to the slowdown. We have to lock the bitmap. And we have to unlock it when we're done. When you're doing direct pixel access through the put pixel and get pixel functions, you have to lock the bitmap. And that takes time. Now if you don't lock the bitmap, it's actually even slower. It takes so long that I wonder if it's even going to run when I do that. So that's the thing. So that's the function that draws the checkerboard. Now after it draws the checkerboard, it does, it sets the target bitmap to bitmap 1. Now bitmap 1 is our bitmap that has the polygon, and we'll go back to the, let's see, where's the Allegro polygon one? Okay, yeah, I'm going to have to reopen that file. So Allegro regular polygon. Now this is the code that does the polygon. I showed you this in my previous video. So it draws a star polygon using very specific setup. So you may not understand all that, but you saw that it does draw the pentagram. So it's meant for star polygons, but it can do other types of polygons. So now here's where it gets interesting. So drawing the checkerboard is done once. Drawing the polygon is done every single frame. So naturally that is the bulk of the program, is redrawing the polygon every time it rotates. So why, but the previous program did that and it still could spin extremely fast. So now why is this program so much slower? And here's the key right here. ALBBM image XOR, and it uses 3 bitmaps. Okay, so I'm going to show you the biggest and most complicated function that you probably never wanted to see in your life. This next function after the chastity checkerboard function, this is complicated. And as I wrote in my comment above it, it's majorly complicated. And that's because it doesn't have a simple memory access. You can't just access the pixels as an integer array like you can do with my own code. This has to do several things. 3 bitmaps are passed to this function. The first bitmap is the receiver that's written to. The other 2 bitmaps are the ones that are read from. So what it does, this function assumes that all 3 images are the exact same size, which they are. It takes the first bitmap and gets its width and height. And here's some comments that don't actually do anything. I can remove that right now. That was from a previous function. And then, okay, I'm fixing my code as I go along. So then it has to lock all the bitmaps so that it gets anywhere near decent speed of access. So it locks bitmap 0 with Allegro lock write only. And notice that it has to get the bitmap format because there's apparently different formats, although I don't know what they are yet. So the first one is only written to, so it's write only. And the other 2 are read only. So bitmaps 0, 1, and 2 are all locked. Then it sets the target bitmap to bitmap 0. And that's because bitmap 0 is being written to, therefore it will be our target bitmap, and it will be targeted by the put pixel function down here. But what happens before that is where it gets really complicated. So after everything's locked, it does this loop and it cycles through everything. So it stores in AL color 1, which stands for Allegro color 1. It gets that pixel at that X and Y coordinate. We're looping through the entire image, all 3 images actually. So it gets in ascending X and Y coordinates. So it gets that color of that pixel of bitmap 1 and stores it in that. It does the same with AL color 2. It gets that pixel from bitmap 2. And then, that's as if that wasn't bad enough, that we have to lock everything and get these 2 pixels from that location in the image. Then you can't simply XOR them together because they're structs. It's a C structure. is what it is. So you have to unmap them to red, green, and blue. So you'll notice I have unsigned char variables and they store what are going to be the separate bytes that are red, green, and blue for all 3 pixels. So first it gets the red, green, and blue, R1, G1, and B1, and then for the first color, and then for the second color it does the same thing with separate variables. And then R0, G0, and B0 here, you see that I XOR the 2 red values to get the final red value, the same with the green and the blue, and then after all of that it has to map that color from those red, green, and blue values into another struct that is the final color, and that final color is written. But that's only 1 pixel. It has to do that for every single pixel of all 3 images. It has to get those 2 pixels from those images and then combine them, XOR them into the final color that we put into the destination image. So now you can start to see why it's slow. And then of course afterwards it has to unlock it. But now the locking and unlocking only happen, well actually they happen every single frame. It happens every time the function's called. So it's no wonder, even though the checkerboard is only drawn once, then every single frame it is drawing a new polygon, clearing the screen, drawing a new polygon that has different points, and it's rotating it every single frame, and then it XORs them together to create the final image that's displayed. Now here's the thing, I can show you an example of, okay, so let's see how it runs here. Yeah, it's kind of slow. Now compare the function that I just showed you that does all of that just to XOR the pixels of the 2 images. Well, I'm going to show you something. I'm going to show you my recent file that I did in a separate video. Now this is an animation file. In fact, this is my most recent one for my main BBM library. My BBM Star Polygon Animation 0. Now this one is complicated, very complicated, it's true. However, I want to show you, now most of the code is just animation related purposes. It's probably still smaller than the Allegro code because it doesn't have a library to initialize. So, but here is the code that does the XOR. This section of code right here is absolutely everything. That is what XORs the 2 images together, because this one uses only the C standard library in my own code, but since every pixel is simply a number, we have P, so basically this image is being XOR'd with these 2. So technically P and P2 are the only images that are being XOR'd here. It's slightly different in this system because I use different variable names. That's a whole other program right there. But the XOR code is simple. We have the X and Y loop in this one just like we do in this one. We still have the same X and Y loop, but look at the difference between this X and Y loop here that has to get the pixels and unmap the pixels, then XOR the pixels, then remap the pixels, then put the pixel. It has to do all of that, whereas mine simply does this. It goes through the whole thing and it has one instruction. This is it. That the pixels pointed to by pointer P at that specific X and Y coordinate, there's my formula that gets that specific coordinate. I've covered that in other videos. It's just a simple XOR operation. That's all. No locking, no unlocking, no mapping, no unmapping, none of that. So here's the thing. After all of that experimenting, I discovered an amazing thing. My code, although complicated, now this one is very interesting. Yeah, I wonder. Yeah. Anyway, but so what I was about to say is what I learned is that although my Allegro programming works and I have it do precisely what I want it to do, it's not only much slower, but it's also very much more complicated. It takes a huge ton of code to do a simple operation that takes forever. So now, this is why the kind of animations I create are probably not suited for a library like Allegro or SDL necessarily, because it's going to basically it's going to have a whole bunch of extra code of locking and unlocking things that takes extra time. So it's very sad. Now, although this is slow, I'm just going to show you for example. Now what happens, I'm going to do a little bit of modifying here. So it uses the same delay there as my previous videos program. So what happens if we comment out the code that does the XOR? Well then, because it's outputting that final output image, it's a blank screen. It's totally black because it doesn't actually have that image there. So instead of drawing bitmap 0, let's try drawing bitmap 1. If we draw bitmap 1, then you see it's just a white pentagram spinning. And notice it's much faster. That's because it's not doing the XOR. It's drawing the polygon every single frame, but it's not having to XOR two images together to make a final one. And then, of course, we can also just draw bitmap 2, which should be our checkerboard. And then, of course, it just draws a checkerboard. It's a still image, therefore, there's no such thing as speed because it's just showing us the same image every single frame. So that's basically it. Is basically how it works. Now I will set this back to the way it was, and we will get it back the way it was. Wait, oh that's right, I named it bitmap instead of bitmap 0. It needs to be bitmap 0. There's a huge difference. Okay, but so although it's slow, you know, it's still kind of neat. Now, you may notice though that in my animations that I've uploaded, my GIF animations to Facebook and such, notice they run very fast. They run a lot faster than this. Well, it's quite simple, because really, when you have an already existing series of images stored in an animation file, the pictures have already been drawn, the frames already exist, therefore speed is no longer an issue. So it gets very interesting, because I could make some changes to this in the future, and I'm also going to change the number of points here. Let's see here. Let's change the number of points to 6, and then let's see if it gives us a hexagram. Yep, it gives us a slow-moving hexagram. So that's actually quite amazing when you think about it. But yes, it's still slower than a regular animation, but still very pretty and probably worth sharing. Although I just thought about something. What happens if I don't have the wait function in there at all? What if I remove the AL rest function? And then let's see how it runs. Well, it's still horribly slow, but it's faster than it was, which is interesting. It might even be running faster if I had a faster computer, but basically if I want fast animations, I pre-generate them with images. So anyway, I hope this video has been enjoyable to some kind of graphics programmer out there. Now I am going to end this video, and then I'm going to back up all my source code I've been working on, but this has been great fun.